This is the Mould effect, discovered by Steve Mould, where beads seem to defy gravity and jump crazily out of a beaker. Today, let's make some observations and then see if those observations can lead us to some kind of an experiment.
What I have here is 65 feet of steel beads that I'm gonna drop from about 6.5 inches. Check this out. Let's drop them from higher and higher heights today and see what happens. They just barely squeak over the top. It's kind of like seeing the water in a siphon. From the top of the table to the floor is a meter. Check it out. Look at that. They shoot over the top.
One of the things I'm starting to notice is that the beads don't go a consistent height as they fly out of the beaker. They kind of just go crazily up and down. But there is sort of a pattern I'm seeing. Is the beads started flying out. When they came out really clean, they fly out really high over the top of the beaker. But then when they get tangled with each other, they get caught and don't fly out quite as high. We can see that here. But then if they're loose, then all of a sudden they start flying out high again.
Here's 2 meters. Watch how high above the lip the beads get. If you notice these little beads, they're starting to shoot over the top a little bit higher. That's so cool. What we get? About that much?
It was at this somewhat sad point of scientific inquiry, when I was measuring length as a square with my fingers, that I realized there had to be a better way to do this. So I slapped a ruler on the back of the beaker and decided to measure height that the beads jump to the distance that the beads fall. From table height to 3 inches, the beads don't really do anything at all. At just over 12 inches, we can see the beads squeak over the top of the beaker, but they never jump over an inch.
Just barely squeaking over the top. Still pretty cool. It's like a long chain polymer.
I was curious if the beads had to actually be in the beaker, so I just pushed them off the table. And check this out, they still jump crazily off.
Here's off the table. It's just over a yard.
Here we can see the inconsistency of the uncoiling of the beads as it jumps from about 1 inches to 3 inches.
Got a little higher that time.
Here we see it drop from just over 3 feet, jumping 3 inches to 5 inches. So the uncoiling and the drop, pretty important.
Here's 2 meters. That one seemed like it got so high. We got to see in the footage.
Here's where having an actual cameraman would come in really helpful. It's pretty blurry, but the best I can tell it's between 6 and 7 inches. I did it again and it just jumped out of the frame, but zooming in, I think we're right around 6 to 7, and for a moment it got up to 8 inches from 2 meters.
I'm gonna go as high as I can. We're a little over 3 meters. Okay, we'll see if we hit the ceiling. Oh wow, it hit it! It hit the ceiling! That means it got over a foot. Wow.
If we graph our results with how far the chain fell on the x-axis and how high it jumped on the y-axis, we see this really wonderful trend occur. When the chain doesn't fall very far, it doesn't jump very high. And as it starts to fall further distances, regardless of how tangled it is, it jumps even higher. So my big question is, how high could it jump at a maximum? Let's try to explain why it jumps at all.
So what happened to explain those results? Oh, wow, it hit it! It's really pretty cool. First off, the beads are all connected, and that's really important. You might think, oh, this is kind of like a siphon, and it is a little bit like a siphon with water. The difference is, though, waters are not all connected. These would be sort of like magnets stuck to each other if it was water. Here, they're actually physically connected, so it's more like a plastic or oobleck. The second thing that's really important is that as the beads go over the side, because of the acceleration due to gravity, they can speed up faster and faster when they have longer distances to fall. And as they go faster and faster and faster, that's gonna influence what happens inside the cup. Now, you would probably think they would just get pulled faster downward because gravity is what's pulling downwards. So it's kind of weird that they would shoot up over the top. That we can explain by the fact that these little beads right here have an interesting property that any two beads you can almost treat like a little bendy rod. So it's a bead and a bead, and there's a little flexibility between them, more than there is here. Because of this inflexibility that exists between any two beads, we can explain the jumping action, I think. The beads, if they're going over the side here, or as we watch them fly over the side, there's a bead that's down, and then it's getting pulled upwards by its neighbor and hopping over the side. But why does it really hop? Here's what's going on. The faster it gets pulled downward here, the faster it gets pulled upward here. And what that does is every time it gets pulled upward, the backside whacks into the bead that's behind it, or in this case, the table for my little demo. And when it hits the table hits it back and it hops up. Now, if it doesn't go very fast, it just trickles over. But if I hit it significantly harder and give it a little flick, we see it hop. And that's what our beads are doing. They're getting pulled up really fast. So they get pulled up really fast, and then they hop when they hit their neighbor over the side. And the faster they're able to move downwards, the faster they get pulled upwards here, and then swap into the table, and then hop over the side. Oh, wow! So I think that kind of explains it. I'm not sure what would happen with different masses. I only have this one side. What do you think? Check out the next experiment somewhere in here. See you soon.